In a previous subsection of these notes, we talked about sampling with replacement, where you put the objects back in before you pick them out again, and sampling without replacement, where you take out an object and then it's not available for picking next time. This time we're going to look at a variant of that, which is sampling without replacement, so we take it out and don't have the choice of it again, but when the order we draw things don't matter. And again, this one will be easiest to explain through using an example. So here's our example. In Lotto, which is the name for the National Lottery in the UK, you can buy a ticket for £2 and choose 6 numbers between 1 and 59. And if the 6 numbers on your ticket are the 6 numbers that come up out of the machine, then you win the jackpot, which is usually somewhere between about £2 and £20 million. And it's shared between all the tickets that get 6 numbers. So if you buy a ticket, what's the probability you win the jackpot? So what's the probability that your 6 numbers are the 6 numbers that come out of the machine? So here we see that the sample space, omega, is the set of all sets of 6 numbers. From 1 to 59, because those are the things that could come out of the machine and could be the winning ticket. And then the event A is your 6 numbers that you picked on your ticket. So the first obvious thing is that the size of A is 1, right? You just bought 1 ticket, and so you've only got 1 chance of winning. The difficult question is, what's the size of omega here, the sample space? So we can think of this in terms of the balls coming out of the machine being sampling without replacement, because you can't get the same ball twice. So the first ball that comes out of the machine has 59 possibilities. Then the second ball that comes out of the machine, it can't be the same as the first one, so it's only 58 possibilities for that ball. Third ball that comes out of the machine, 57 possibilities. 55, 54. And you will recognize that as being a falling factorial, 59 to the 6th underline. However, that's not the right answer, right? Because the same set of 6 numbers could come out of the machine in any order. If the numbers came out 1, 2, 3, 4, 5, 6, that would be the same set of numbers as if they came out 1, 2, 3, 4, 6, 5. It'd still be the same ticket that won, even though the balls came out of the machine in a different order. Similarly, if it came out as 6, 5, 4, 3, 2, 1. So the problem here is that we've overcounted. Each set of 6 numbers, we've counted a number of different times, depending on what order the things come out. How many times have we counted each one? Well, it's the number of ways of ordering the 6 balls, right? For every way that the 6 balls could be ordered, we've counted it, and that's 6 factorial. We know that from the previous section. That's the number of ways to order the 6 balls that come out is 6 times 5 times 4 times 3 times 2 times 1 equals 6 factorial. So there are 59 to the falling factorial 6 ways the ball has come out, but each set of balls has been counted 6 factorial times. So that's the number of possible outcomes here, of possible winning tickets. And I put that into my calculator earlier, and that came out as about 45 million. You might want to bear in mind this decision when deciding whether it's worth your money playing the lotto or not. And so we see that the probability of A is, as always, number of elements in A over number of elements in omega. A was 1, omega was about 45 million, so we've got about a 1 in 45 million chance of winning the lotto, which, if I get my number of zeros right, is, I think, that many zeros. So quite a small possibility. So there's a notation we use here, which this number, 59 to the 6 falling factorial over 6 factorial, we call this thing. A set of brackets with 59 on the top and 6 on the bottom. So that notation is that n choose k is n to the falling factorial k over k factorial. Or if you like, it's n minus 1 down to n minus k plus 1. Remember, that's k terms altogether. Over k minus 1 to 1. And that's the number of ways to choose k objects from n with without replacement, and where the order doesn't matter. We call that thing the binomial coefficient. That's its proper fancy name. It's called the binomial coefficient. If you want to look it up in a book, you'll have to search for binomial coefficient. But actually, when we speak out loud, we normally just say n choose k, because you've got n objects and you want to choose k of them in a way where you don't care about the order. There's perhaps one other thing to briefly mention here, which is that since n choose k is n falling factorial k over k factorial, you'll remember that n k falling factorial can be written as n to the k over n minus k factorial. So if we want to, we can write the binomial coefficient, sorry, that's not right, like that in terms of factorial functions, because the first two terms there are n falling factorial k. It's just that that's sometimes a useful expression to have available to you. Let's see another example of how to do this, how to use this. This is example 3.7. You're dealt a hand of 13 cards from a deck of 52 cards. What is the probability that you have the ace, king, queen, and jack of spades? So as always, we need to say what's the sample space, what's our event. So omega is the set of all 13 card hands from the 52 card deck. And A, the event we're interested, is all 13 card hands that include the ace, king, queen, jack of spades. I'll abbreviate that as AKQJ, ace, king, queen, jack of spades. So as always, what we need to do is we need to say how many elements are in each of these sets. So by what we've just said about the binomial coefficient, it's clear that choosing 13 hands from 52 is 52 choose 13, the binomial coefficient, 52 choose 13. What about our event A, that we have the ace, king, queen, jack of spades? So one way to think about this is pretend you've been given the ace, king, queen, jack of spades. Then what can you say about the rest of your hand? Well, if you've had those ace, king, queen, jack of spades 4 cards, you need another 13 minus 4 cards, which is 9 cards. So you need to get another 9 cards. And how many cards are available? Well, there were 52 cards in the pack. You've got the ace, king, queen, jack of spades, so there are 48 left. So the number of hands that includes the ace, king, queen, jack of spades is, once you've got the ace, king, queen, jack of spades, how many ways can you fill up the rest of your hand And you can fill up the rest of your hand in 48 choose 9 different ways. So the probability of A, that you have all those cards, is the number of elements in A, 48 choose 9, number of elements in omega, 52 choose 13. Now, at this stage, you might think that you just have to mash all that into your calculator, but actually we can do a little bit of this by hand if we want to, which is that we can write out the terms. So at the top we've got 48 times 47 times 41 times 0 over 9, 8, 7, 6, 5, 4, 3, 2, 1. And then on the bottom, we've got 52 times 51 times, and if you work it out, that also goes down to 41 times 40. And on the bottom, we've got 13 factorial, which is 13 times 12 times. And you'll see we actually get quite a lot of cancellation here. Right, on the top, this 9, 8, 7, 6, 5, 4, 3, 2, 1 cancels out with a 9, 8, 7, 6, 5, 4, 3, 2, 1 on the bottom. And this 48, 47, all the way down to 40 on the top cancels out with a 48, 47, 41 down to 40 on the bottom. Right. And then finally, this 13, 12, 11, 10 on the bottom of the fraction. You know, if in a big fraction you're on the bottom and you're on the bottom of that fraction, it's like you're on the top. And so that can come upstairs. And so when we work all that out, what we've actually got left is 13 times 12 times 11 times 10, which is the bit on the very bottom that didn't get cancelled out by the 9, 8, 7, 6, 5, 4, 3, 2, 1. And on the bottom, we've got 52 times 51 times 50 times 49, which was the stuff on the bottom that wasn't cancelled out by the 48, 47, 46, 45, 44, 43, 42, 41, 40. So actually we can neaten it up quite a bit by hand. And, you know, at that stage you probably do want to put that into your calculator. It's 0.0026, which apparently is very roughly 1 time in every 380 hands. So if you deal yourself a hand of 13 cards, you need to do so about 380 times before one of them has the ace, king, queen, jack of spades. Finally, one last thing that we can mention about binomial coefficients while we're here, kind of useful fact, is that n choose k and n choose n minus k are the same number. And there are two different ways you can prove this. One way is pretend that you've got n balls and you want to paint k red and k blue, the rest blue, sorry, n balls. Paint k red and the remaining n minus k blue. How many ways can we do that? Well, we could say pick k balls and paint them red, and then paint the rest blue. So how many ways can we choose the red balls? It's n choose k. So this is from choosing the red balls and then just painting all the rest blue. On the other hand, your way to do it is you could choose n minus k blue balls and paint the rest red. Right, so that could be n minus k from if you choose the blue balls. As in, choose the balls you want to paint blue and paint the rest red. And because we've counted the same thing in two different ways, right? The way to paint k red balls and n minus k blue balls. Because we've counted the same thing twice, these numbers must be the same. Alternatively, you could go to the statement with the factorials we had before. We had that n choose k equals n factorial n minus k factorial k factorial. On the other hand, n choose n minus k is n factorial over n minus n minus k. N minus n minus k is just k. So we get that. And those are obviously the same thing, right? We've just changed the order of the two things on the bottom, but they're equal to each other. You're invited to think about which one of those two proofs you prefer. I much prefer the red ball and blue ball version because it works if I don't remember the factorial function, and it kind of tells me why these two numbers are true. That's a useful fact about the binomial coefficient that you might want to remember.